You know, what is the most complicated thing on your network? Not counting people and all that good stuff, but what do you have on your network that probably has more complexity than anything else? Well, if you look down the table, you probably see a pretty quick answer here. That's these little silly antennas, right? You wouldn't think that these things would really be that complex, but the mathematics, the physics involved with antenna theory is really pretty darn intense. Now, this is Networking 101, so I'm going to go into some of the basics of antenna theory, and I mean just the really basic type of stuff, because you can actually get a PhD in antennas, and you can really dig into the depths of it. There's tons of equations, Maxwell equations, all that stuff. I'm not going to mess with any of that stuff because it just gets very complex. Show you the basics and what makes these things pretty groovy. Well, a couple things, visually speaking, anytime you're going to look at an antenna, you can almost tell exactly what it's going to do based upon the shape. If you looked at how this one looked right here, right, you'd say, well, you know, kind of looks like it's like a gun or something, so it's probably going to shoot the signal that direction, and that's true. Or you look at something like this one here, this little tiny one. What's this one going to do? Well, it's going to radiate out in this way. In the same way with this little rubber duck antenna, right, that you see a lot on like your home devices and stuff. You know, what's the signal going to do? Well, it's going to be 360 degrees. Or this patch panel, right? This is something you'd mount on a wall or a ceiling because it's a directional antenna. So I can put this up kind of high, and I'm going to get my radiation here. Now, an important thing to understand about antennas is every little tiny thing matters. Everything you do on antennas matters completely, right? Because these things, we're used to looking at technology in a 2D space, right? We're used to looking at bits and bytes and everything very two-dimensionally how they work. Antennas live in a 3D space. Everything that they do works on a horizontal plane and a vertical plane. So when you go to buy an antenna, typically, now check this out on the screen, typically what you're going to do is you're going to get what they call a radar plot. And this antenna plot itself is going to tell you what your radiated effective signal is going to be. Now your antenna is going to set, let me turn this like this, your antenna will live right here in the middle. The main part here, this is what you call the main lobe, and that's where your radiation is. Now this is a main lobe for a Yagi antenna. So if you basically laid it down there, that's pretty much, or let me put it up here, it's going to be a little bit easier to see. It is pretty much going to look like this. Your main lobe is going to shoot out this way. These are actually what we call side lobes, and really kind of undesired. And these are your back end lobes, right? These are actually just kind of radiation that's going to leak out kind of away from here, or you're going to get through the cables and stuff. But this is where you're going to really get that boost. This is what you're going to see vertically on this antenna. You're also going to have a horizontal plane antenna here. So what you're going to see in this area, you see these live in three-dimensional space. And that's how you're going to know what right antenna to put in the right format and stuff. There are a lot of equations behind this. And how do these electrons move? It has to do with really how you're actually moving negative particles down these things to actually get them to radiate out. But the important thing to understand about any antenna, every little thing matters. You change the temperature outside, you mount this outside, it's going to change how this antenna works. If your alignment's just a little bit off, if this antenna is like pointing just a little bit there, it's going to matter. Why? Because you look at how this lobe is, you're going to be off target. I want to hit something on this end. The shape of these things matters enormously. So, you know, if you look at something even like, you know, a satellite dish, and you're looking at how, you know, how does that thing work? How does that radiate out and get interest in? Well, you're looking at how the radiation is bouncing back and forth. You're going to get this incredibly powerful signal, you know, so it's going to, you know, really radiate out. But then your return signal wants to come back really weak, really, really tiny. And so I need something bigger to catch that and send that in. Why are satellite antennas so big? Because satellites are 22,500 miles in the air. So we got to be able to really catch and discern a very, very small minimal signal. Now, like I said before, everything you do on antennas is important. So when you look at, I've got a few different examples here, but they're here for a pretty important reason. You see how this one is? This one will couple directly to your wireless access point itself. It plugs in, and why these are awesome, why they're great, same way with these rubber ducks, is you don't have much loss in them. See, antennas are designed around a concept we call gain. And so gain, dBs, we measure, radiated power, isotropic power, in what we call decibels. And we may remember hearing that like in music and stuff like that, and the more decibels, baby, crank it up, that's good stuff. And it's kind of the same on wireless too, but because the wireless we use today is unlicensed, it's in what we call the industrial, scientific, and medical band, everybody has equal access to it. So we have to be very concerned about how much dBs we're putting out because we're responsible for that. So we can't just blast everything out there, or we have, people in, black suits and ties knocking at the door. You don't want seconds on that. So what we're doing is we're looking at an antenna. Let's say I've got an access point here. And my access point is, let's say it's 11 dB. And so we're going to say, well, I got 11 dB AP here, and I need to add some more power to it. I need to get some more, energy out to here. I can plug in a new antenna, and maybe that antenna says, well, the gain on that antenna is maybe +6, let's just say hypothetically. So it's a 6 dB antenna. This antenna is 6 dB. From this point here, you see this? From that point there to that point there, that is 6 dB. That's the gain. Now, when you start adding things onto it, you start losing. You have to start subtracting from this amount. dBs are additive. So if I say that I need to plug one in, so if I have to add on like this little lightning arrestor here, which is a good thing to add on here, if I plug this in to this what we call pigtail, this causes a dB loss, and they're all rated. They'll say how much dBs that they're actually going to subtract from your number so you know really what you're getting. This cable, when you look at how long this pigtail, it's a pretty darn long pigtail here. Be careful how long you make these. You have loss on every few inches of this cable. Every few little bit is going to count in dB loss. So the longer this cable is, the less your signal is. I've seen actually designs where you've got so much loss on the cable that by the time you actually get it back in here, you're almost at a negative, and it doesn't do anything, because you plug them in and you're like, that antenna was horrible. Well, we're used in the networking side of grabbing, cables and making cables long and, having all this excess. You can't do that with wireless antennas. You can't. Every inch, every centimeter counts on how well these antennas are going to perform. It's all about the performance factors. This pigtail, this is what we call termination. It's incredibly important to use very, very high quality terminations on here. Once again, you're adding something to this. Anytime you add on, you're going to get lost. So this counts, lightning arresters count. Everything counts on how we're building up this antenna, because the most important thing to understand when it comes to wireless is it can be somewhat unpredictable because you're going to have variances in weather. You're going to have variances in how your alignment's going to set up. You're going to have variances in aging and components and all these type of things. We want to pull as many of those variables out as possible. So get the antenna you need. Don't overpower it. Don't think, well, I need to get this signal over to the other building, so I'm going to use what we call this Yagi antenna and blast this signal out to send this over. This is pretty impractical for anything except connecting usually buildings together, right? Pick out exactly what you need, exactly the right type of antenna. Heck, even these, if you look at them, they look completely different. Stamped on these, I know that you can see right here, where you can actually see that it actually does have a marker on it that's actually showing you what the dB ratings are. In all our devices, all your antennas are going to have a marker, and they're going to tell you what frequency band they're optimized in, and your radar plot's going to show that as well. So antenna theory, man, it gets complicated. It's very cool. I love this stuff, man. And if you really like messing around with antenna theory, you want to dig into it a little bit more, I tell you what, I cannot recommend a website higher than antenna-theory.com. The guy who does this, very cool type of cat, right? I mean, you can get lost in mathematics on these things and physics and really impress your friends with some pretty heavy-duty deep knowledge and stuff. This guy doesn't do that. He's like, okay, I'm not going to use as much math as probably a lot of people do, but here's how this stuff works. And this is why this is designed. Great, great website to really dig into the meat and taters of antennas.